Welcome to MIPI DevCon 2020. Thanks for joining. We're glad to have you with us today. Feel free to engage with the presenters and attendees by using the engagement tools at the footer of your screen. Click Q&A to engage with presenters and group chat to communicate with the attendees. You can simply minimize or maximize each of these icons with one click. To see the agenda, sessions, and demos, click on the Call to Action icon. Enjoy the conference.
Good morning, good afternoon, good evening, ladies and gentlemen. Thank you for joining us in the first virtual MIPI DevCon. This is a joint presentation between Renesas and Mixel, and we will be talking about automotive SoC designs and challenges, focusing today on high-speed MIPI CSI-2 interface, which meets automotive ASIL-B. This is the MIPI CSI-2 IP which Mixel provided and Renesas has integrated successfully in their auto SoC. Let me introduce you to Serge Di Matteo. He's the Functional Safety Director at Renesas, and myself, I'm Ahmed Ella, the General Manager at Mixel. We will start by Serge giving us a general overview about automotive SoC design. Then he will talk about specifics in the Renesas SoC and the challenges in their SoC development. Next, I will be covering the MIPI IP design for automotive. The mic is yours, Serge.
Good morning, ladies and gentlemen. I'm going to provide you a very general overview about a system on chip we have developed for signal acquisition and signal conditioning according to ISO 26222 for data acquisition, for target acquisition in automotive applications, and by integrating a MIPI CSI-2 interface for transferring the bulk data, the huge amount of data that's coming from the sensors processed and therefore transferred to the ECU for further processing. I want to highlight to you the main difference there is in using such interface for infotainment application with respect to functional safety application, where we have quite high demanding requirements in terms of failure rates. We have quite high demanding requirements in terms of temperature range of operation, that we have to achieve up to 150 degrees junction temperature for this system on chip. And therefore this justifies or requires quite intensive thermal performance analysis, power optimization, and last but not least, system level diagnostic capability. We have integrated an overall amount of more than 50 safety mechanisms in this system on chip for supporting, for getting compliance to ISO 26222. You can see the main functions as included in this system on chip. On the right bottom side, we have the interface between the system on chip and the ECU that is realized by the MIPI CSI-2 interface. Through this interface that has been developed as an IP in compliance to ISO 26222 ASIL-B, we transfer up to 10 gigabit per second of data as acquired by the row of sensors, multi-channel sensors that you can see on the left side of the picture. The signals, the low-level signals coming from this row of sensors are amplified by a row of amplifiers, transimpedance amplifiers for being more precise. Then these are the signals are converted into a digital format and then pre-processed for allowing the external ECU to determine the characteristics of the targets according to the timing of the acquisition and to other characteristics of the signals. there is a layer of functional safety mechanism in this system on chip as a part of the support functions that allows, that monitors, constantly monitors that all the blocks are performing according to their specification. We have more than 50 safety mechanisms included into this system on chip. The colors highlight the digital functions in green, and instead the analog functions are in orange, highlighted in orange. Inside the digital functions, we have a quite significant amount of memory components, static RAMs, that, by the way, is a source of transient failures. Now, as you can imagine, so many channels that independently process the signal generates heat. Therefore, the analysis of the thermal performance of this device is an important part of the development process. As you can see in this slide, on the right side, there are some outcomes of the thermal simulations according to the 3D modeling that we have used for doing the thermal simulations. And moreover, there is also a quite, there was a quite significant effort in analyzing the timing performances for allowing precision and accuracy of the acquisition of the target at the level of centimeters. The analog front end is characterized by the development of ultra low noise, high bandwidth sensor sensing amplifier and by high speed ADC that converts data at a rate of hundreds of megasamples per second. And these data, once processed, are transferred through the MIPI CS2 data interface to the external ECU. In parallel and concurrently, the ECU can access the system on chip through a safe SPI interface for reading and writing the configuration registers, and therefore for changing on the fly the configuration and the functionality of the system on chip. Since in this system on chip we have a quite significant amount of static RAM and memory cells, these are sensitive to transient failures, and therefore we have implemented a quite numerous set of detection mechanism, failure detection mechanism, for ensuring that the transient failures do not corrupt the data. We will see later on what kind of measures we have implemented, more in details. And in terms of timing generation and signal integrity check, we have largely used the 3D modeling of the signals and the routing through the silicon, through the package, down to the pin, for checking that the signal integrity was under control, and for ensuring that the contribution to the signal to noise ratio coming from parasitic elements is under control. Such a system on chip is a unique challenge to Renesas, because we have had many first times. We have had first time use of 28 nanometer technology, first time use of system in package with flip chip in a BGA package, and first time use of MIPI CSI-2 interface in an automotive and functional safety project. In terms of product development, we went through the ISO 26222 through the normative of these standards, all the normatives for being compliant. Since this is an hardware element, the only part of the ISO 26222 that we have not considered is part 6, software, related to software development, because we don't have any issue inside. Of course, we have the qualification plan according to the ASIL-B 100, and the overall development process is certified according to the Automotive quality standard, that is ATF 16949. And one specific challenge, as I have mentioned already, is the quite high software error rate caused by the quite significant amount of memory cells we have in this AC. That is around about tens of megabits, and this has generated, has caused about more than 20 kFit to be addressed with quite numerous set of countermeasures that we will see in the next slides. A very effective strategy for mitigating the software rates includes two sets of countermeasures: mitigating measures and detecting measures. In the range of mitigating measures, we have we have replaced the standard MOR compound and other materials, like also the bumps, with ultra low alpha material. This material is highly purified and reduces by several order of magnitudes the flux of alpha particles that are one of the components, one of the causes of software rates. The other causes are the high-speed neutron. But this cannot be mitigated. We have to deal with that. Second additional mitigation measure is the compilation of the SRAM system instances with a high level of multiplexing. This allows to have the memory cells belonging to the same world far away each other in the memory matrix, and therefore this allows to convert all multiple cell upset, multiple cell bit flip, into single bit cells into the same little world. There is an example I will show a couple of slides later. In terms of detecting measures, we have the instantiation of the 1-bit error correction and 2-bit error detection for each SRAM instance, plus checksum for covering all the sub-functions of the digital logic that are not addressed by the ECC EDC layers. In these slides, I can show to you what is the problem. On the left side, you see typical cell matrix organization memory, where an alpha particle or an high-speed neutron causes the bit flip of one memory cells. The majority of these events are just bit flip, single bit flip. However, sometimes, especially when there is a high energetic particle, it may be possible to have multiple bit flip. In this case, this example on the right side of this slide, so we have up to 6 bit flips. In this example, if there are no specific architectural measures or compilation measures of the SRAM, we see that such event causes 2-bit flip for each memory word. And according to the wrapper that we have, this can be just detected, not connected. Even worse, in case we have more than 2 bit flips per word, this cannot be detected and therefore it may be dangerous to transfer wrong data to the application. How to solve this issue? With the set of combined countermeasures, as I said, the compilation of the SRAM with a specific multiplexer option allows to use the LSB, the low significant bit of the address, for spreading the data contents of each addressable word. It is spread through the whole matrix. This means that when an event like you see on the right side of 6 bit flips occurs, in reality this generates 6 bit flips, but distributed through 6 different addresses. And for each address, this is manifested as a single bit flip that can be detected and corrected. Therefore, we have not only a fail-safe operation, but also fail-operative condition. Thank you so much for your attention, and I move the ball back to Ella.
Thank you, Serge, for these useful insights on automotive SoC design. Let me talk about Mixel's MIPI interface in the auto SoC, and as an IP provider, what differences would that be for us? So if you're interested in auto-grade IPs and you still have not figured out what you need to do, you should find this helpful to you. From our experience, the auto-grade IP is different from standard IP in 4 domains: reliability, safety, testability, and performance. The differences here are in the process, levels, certifications, and expectations. Obviously, not that these 4 domains do not exist in standard IP. The auto IP is verified with high parts per million target, and its critical specifications are met according to the CPK distribution. To comply with auto IP requirements, your development process has to follow a well-established quality management system, QMS. This is to ensure the quality of your product is consistent and follows a well-defined process. At Mixel, we have developed our QMS based on the ISO 9001 standard and certified it through DECRA. The ISO 9000 covers all the clauses of the IATF 16949, which is required by the automotive compliance. On top of that, we developed a functional safety culture to comply with the ISO 26262 standard. The first domain we're going to be talking about today is reliability. How does reliability relate to safety? You would think that they correlate, but that is not a must. In reality, reliability is not a must to be safe. As Serge always tells me, think about a broken elevator which doesn't function. It is safe because no one can get hurt in it, but for sure it is not reliable. Talking about reliability in auto, we have the AEC Q100 standard, which defines the ambient temperature of your chip. Usually the junction temperature can be higher. So in case the requirement is AEC Q100 grade 1 with 125 Celsius of ambient temperature, then our IP design would accommodate for junction temperature of 150 Celsius. The second point from a reliability perspective is the mission profile of the environmental sensor. This requires reliability assessment of permanent failures caused by electromigration and aging effects. The third point is the design margins required. For QM-based chips, our CPK target is 1, which is the well-known 3 sigma design. While in ASIL products, the CPK could range from 1 to 2. 2 is equivalent to 6 sigma margins. In this case, for this Renesas SoC, our target was 5 sigma design. On top of that, for auto-grade IP, we have extended PVT sign-off corners, besides simulations based on the mission profile of the SoC, such as aging and self-heating. The second and most popular domain we're going to be talking about is the functional safety. Of course, we cannot cover everything concerning functional safety here, but we will focus on a few highlights. Our IP is developed as a safety element out of context. And the well-known challenge for IP vendors is that we do not have any prior knowledge of the component. So what can we do? We have to make some assumptions. We assume safety requirements, which need to be general to support a wide range of customer expectations. Additionally, we populate all the assumptions of use, the AOU, such as the target ASIL, the operating conditions for PHY, the best modes, the temperature mission profile, and the source of baseline failure rate. Another topic we'll cover in safety is the design failure mode and effect analysis, for short, the DFMEA. It's a method to assess systematic failures, both internal and external. Each failure effect is given a severity rating and correlated with the risk associated. What is the result from that? We assign corrective actions to improve the detection and prevention of high and medium risk failures. Besides, we create a database which is shared with the component level, the SOC, for the risk analysis on chip level. A second step to achieve the functional safety of a device is developing the failure modes and diagnostic analysis, for short, the FMEDA. The FMEDA is to assess random hardware faults, and its main output is calculating single point and latent fault metrics. From the FMEDA, the failure rates are determined. There are permanent random faults and transient random faults, which are based on the process technology and the type of the circuitry being analyzed. The safety mechanisms in this system are analyzed both internal and external. Internal, such as loopback test and initialization, and startup, or the PLL lock detector and frequency range monitor. External mechanism would be such as the D-PHY receiver on the other side of the link, which has a sync detection, or the CSI receiver controller on the other side of the link, which has CRC and ECC checks, and also system-level checks in the receiver SOC chip, such as the watchdog timer. The final failure rate, FIT, is linked with the technology, package, and temperature. The third step we'll be covering today for achieving functional safety compliance is the safety manual. This is where we captured and documented all the product-related items, the assumptions of use, the assumed hardware safety requirements, the safety goal violations, the internal and external safety mechanisms, and the summary on our safety analysis, the DFMEA and the FMEDA. In addition to the product-related items, we tailored the safety lifecycle for our IP development process. This was a brief on the functional safety highlights. We can advance to talking about the third domain, which is testability. At Mixel, we have developed proprietary configurations which are optimized for automotive applications and production testing. We call them TX Plus and RX Plus, and they exist for both CSI and DSI. These configurations allow us to achieve higher product ASIL grades, and they enable full loopback testing, which would allow periodic checking of faults and support production testing. Renesas utilized the testing features embedded in the TX Plus MIPI interface in both the lab validation and the ATE validation. In this slide, we can see a snapshot of the Renesas lab testing their chip, which includes the MIPI interface. The fourth and last domain we'll be covering today is performance. For future cars, we need more powerful electronics. More and more functions in the car are being replaced by sensors, and these in turn require higher bandwidth to account for higher sensor resolution and higher dynamic range. With our latest CD5 generation, the MIPI interface bandwidth can reach up to 30 gigabit per second. In this particular SoC, the bandwidth requirement was 10 gigabit per second. Other than bandwidth, IP area is becoming more important in auto chips, especially as they start to target the most advanced nodes. We help with risk mitigation as we provide an integrated MIPI subsystem, which includes the PHY, the controller, and the verification environment. Besides, our IPs are silicon proven in a wide range of foundries and process nodes. To wrap it up, Nexel offers you world-class knowledge of MIPI IP and SoC integration best practices, and most importantly, how to safely integrate the IP into your SoC. We also provide on-chip safety mechanisms to help you achieve higher system ASILs. Our integrated MIPI CSI-TX Plus interface has been successfully deployed in the Renesas SoC. Our auto-grade IP can be provided to support ASIL-B and ASIL-D. We also support AEC-Q100 temperature grades 1 and 2. Our CPK target can meet a range from 1 to 2, depending on the SoC requirements. And our functional safety offerings are offered in 3 levels. The first one is the DFME only. The second level is what is called ASIL Ready, which includes the FMEDA and the safety manual with the ASIL Ready certification. And the third level, which is the most important for auto compliance, is the full ISO 26262 certification. To know more about our MIPI IP offerings, you can check the links we have added in the links section below in the platform. Thank you for your time. We'll secure the last few minutes for the questions and answers, but also please stay tuned after the presentation. We have a demo for you showing our IPs integrated in our customer products.
Thanks, Serge. Thanks, Ella. I encourage you to pose your questions in the Q&A pane, and I do see that we have some coming in. First question, why is the standard MIPI CSI-2 data protection not sufficient?
So Serge, please go ahead. Thank you, David, for the question.
In the data format that just covers the random and permanent fails between the end-to-end communication channel, that is the channel between the CLC generation and the CLC checker. This does not cover both the MIPI interfaces, and moreover does not cover all the logic that is used for transferring the data. This is why we have added an additional layer, an additional protection layer with a 32-bit CLC for covering these the additional failure modes that we may have in the communication channels.
Thank you, Serge. Next question. How is MIPI D-PHY adoption for automotive applications coming along?
Within the last decade, we have seen through our customers, the D-PHY adoption in auto is steadily growing. The graph did significantly increase in the last maybe 2 to 3 years, mainly the CSI-2 camera sensor applications, but also you lately see DSI application demand picking up as well. So we do see a lot of D-PHY adoption in the automotive application lately.
Thanks. Have time for one quick question. Which nodes has Nexel Silicon proven D-PHY? How about for auto applications?
Sure, yeah. So like Nexel, we do have a wide range of silicon-proven MIPI PHYs from like 8 different process fabs and 9 different technology nodes, starting from 180 nanometer to the most advanced FinFET processes. And we have seen similar similar range for auto. We do have similar range for auto PHYs. Thank you.
Thanks. I appreciate that. We are actually out of time. I do encourage you to go back to the Engagement Hub to see what is coming up next on the agenda, and we'll move over to the Mixel demo. Thanks again to Mixel and Renaissance.
Thank you.
Thank you.